Hello, my name's Stephen Judkins. I'm a fairly new employee here at Mercury, and I am giving a talk about a project I just did. It's about source code transformation, automatic refactoring. First, disclaimer. I don't know what's going on. There's a wide variety of tools out here. I evaluated some of them to a little degree. Some of them not at all. Some of them were bit rot and wouldn't compile. These seem like good tools. None of them, when I evaluated, did exactly what I wanted in a way that was easy or seemed straightforward. None of them had especially good documentation. But retry seems fairly commonly used. So some context is I am working on a large whole code-based refactoring right now, and there's a few straightforward mechanical transformations I had to make that were pretty slow and cumbersome, and having to do them made the entire process really slow and sort of more importantly, like annoying to reverse. If you spent an hour on 5 files changing this, then you realize you have to back it out. That's just kind of emotionally brutalizing. So, what I ended up doing is writing a tool that used this library called GHC AST. And other refactoring tools are based on this. And this kind of idea here is pretty simple. It has a parser and a generator. And if you do not do any transformation inside, then it will print out exactly the Haskell code that it parsed. So ideally, it makes its transformations like the git diffs look as clean as possible. But sort of the hard part is the transformation between different ASTs inside. I'll talk about that. So it uses GHC's parser, and data types is tightly coupled to a GHC version, or at least like GHC minor version. Everything, all the metadata, it's more like a concrete syntax tree. It keeps all the metadata, the comments, positions, all sorts of stuff. So it's, again, makes the changes minimal. So some complicated wrinkles here is that the GHC AST is from the Trees That Grow paper that Mitchell just discussed. Is parameterized by a per phase type family, which means the types you see in it are not in the file of the main AST, but in the file of the type family that is parameterized. It's just more complicated. It's kind of like, it takes a little work to get there, but eventually you can find the types. I found just telling Haskell compiler to like tell you what type it is will help you find and do it. This way that each phase can hang on different information. So like the parsing phase, the type checking phase, the code generation phase, the information from the previous phases can be kept there while you're still using the same basic AST through and through in a type-safe way. GHC AST uses the data from the first or near the first parsing phase. And so you have the tree that has no type checking, no type information, no import resolution, just a simple, like names, simple qualification. So, you work with what you have in one module at a time. Like this approach lets you go and make straightforward transformations, what you know, but if you have a type that's type alien somewhere else, it doesn't know what that means. They're just the names in the source are the names you have to work with. Another tricky part is location, the annotation tagging that Mitchell just discussed. Tons of stuff has a location attached to it. One thing I found doing these transformations of these ASTs, 1 minute, it's tricky to get right. Reuse existing notations you can. You can build illegal ASTs that generate garbage code, which kind of sucks. There's an API to not do this, but it's not very well documented, so I didn't use that. Just transform the AST data type, again, is straightforward. It's really just a lot like the what Mitchell just presented, the code he wrote by hand for small language. There's more to it, but not all that much more. It's fairly straightforward, so everything is there. This a very simple expression is like a lot of stuff to go through. I found using pattern synonyms and view patterns, exactly like Mitchell just recommended, were like really easy way to clean it up and make these transformations through the tree a lot easier to grok. And recursing all these things like a function definition, they're kind of like linked lists. They're very kind of deep list-like data structures, and the tree-like, but sort of degenerate trees. So recursing to find stuff works well. That was like a good pattern. Here's basically just kind of the example of the meat of the code I wrote. This was maybe several days of work for not much code, but it's as you can see, it's like it's not a crazy thing. And all this does, you have it comments here showing each transformation I'm making, and this can go through and recurse and do like an entire value type signature and change it based on various transformations if the ones at the very end, the tip of the tail, are the right type signature and things matches. Yeah, so it actually pretty reasonable to do, not all that much code, just poorly documented, and uses the type families to make things tricky and the locations to make things tricky too. But yeah, if you're at Mercury, I'd love to, there's a PR with this code in it if you'd love to look at it. If you're not at Mercury, I am sure it'd be okay if I shared this. So I don't know. Max is nodding. All right, I think that's all. I guess no time for questions, but all right. Thank you.